a little bit more than that, obviously, because otherwise there wouldn't be a whole course. But it all comes down to your understanding of the concept of slope. So that's good. You're kind of grounded in your own reality here. So tangent line to a curve or a function. I'll just keep it simple. Here's a curve. Here's an example of a tangent line to that curve. All right. Touches the curve at one location. All right, touches the curve at one location. All right, there's infinitely many possible tangent lines for a continuous function. So I could put that anywhere, but that's the most aesthetically pleasing, I guess, place to put it. All right. Tangent is, bless you, is a derivative of the Latin word tangere, which means to touch. So that's the origin story behind that. Because I know you're all pining for that definition. A secant. All right, a secant intersects a curve, touching it in more than one location. So secant, I'll keep it simple, intersects a curve more than once. What our job is going to be is to investigate the slopes that are generated based off of those intersections. All right, so you'll have the tangent line. All right, the tangent line is, all right, it's going to touch in one location. How can you figure out the slope? Same idea with secant. Now the big question becomes, well, all right, if that's the case, then I know how to find the slope of a line passing between 2 points, 3 points if they're all on the same line. But how do I find the slope at a single point? Change of y over change in x, it would be indeterminate. All right, that ties back to the last unit when we talked about indeterminate in the form of a limit. All right, there's a reason why we're talking about limits and going into this concept of slope. It's going to tie together in a very meaningful way and drive home the whole concept of what is known as a derivative. All right, so what I'm going to do is just kind of get you started on the activity, and you're going to spend the rest of class, and if it spills over into tomorrow, that amount of time to complete the activity. All right, so this is going to be a tear out situation. All right, so you're going to turn this in at the end of class tomorrow. All right, and I'm going to be checking it for accuracy, so you're going to want to take your time and be careful with it. I have rulers and all that stuff, but I want to get you started on it, so at least you have a sense of what the pathway is. All right, so x squared, very easy to graph. And if you're not going to be here tomorrow for some reason, then you just turn it in the next time you are here. I use the 149 approach for graphing parabolas, so I avoid using the calculator. Of course, the drawing of the curve part has always been a little bit of an issue for me. It's not really that important that your curve looks beautiful. Yeah, so this app autocorrects my lines, but it doesn't autocorrect my parabolas, so you get a little taste of what my real quality drawings look like. Nerve damage will do that. Draw secant, really kind of sucks when you just flat out lose feeling in extremities. Oh, so then you know.
Yeah.
Yeah, it sucks, right?
Yeah.
I mean, you're in the early parts of it, but
Sure.
flash forward. Yeah, I've been in that position. I was home, cut my hand, and that's not how I caused the nerve damage, but I was bleeding profusely. But I was at home and I didn't want to go to the hospital myself, so I duct taped my hand back together, and then duct taped it to the wall because I see how you're holding it up vertically so that you don't have the blood pressure issue, and went to sleep. Yeah. Next morning, the bleeding stopped, and I was like, all right, this is good. It really wasn't the hand, it was actually my thumb. I cut the tip of my thumb off. Kind of. But it's kind of weird. You really can't see it except for like just the little remnants of where the scar was because most of the scar ended up under the fingernail.
Is this being recorded?
Yeah. I mean, I was cutting a shallot, so it slipped off. Yeah, like shallots will get you any time. Like if you've ever cut a shallot, it's like cutting an onion, except the skin is very slippery, and so if you don't get a bite into the shallot, it goes right off the edge. Yeah, it went right off the edge. I didn't mean to steal your thunder because you're like dying over there, but. All right, so draw a secant line 1 that passes through the points -3, 9, and 2, 4. So I did that. Pivot the secant so that point B, so I'll label it point A. Point B goes through 1, 1. So I'll do it in a different color here, make it look nice. It's going to go through, it starts at -3, 9, and then goes through 1, 1. All right, so that's my second point, quote unquote B. All right, you could denote it differently if you want to call it like B prime. Or you could label it any way you want, really. But then the next one after that is going to go through 0, 0. And in the table, what's going to happen? So you're going to get all these line segments. It's going to look wonderful. It's going to look like this, except for that you won't have the awful looking. You're not going to have the awful looking parabola, but you'll have something that looks like that. It's just going to look a lot better on your paper. And what you're going to do is compute the slopes for each of those. All right. So you have to find certain ingredients like A, coordinates for point A and F of A. Don't get too alarmed by that. The A is the X value of a coordinate. F of A is what you get when you plug A into the function, also known as the what value of the coordinate, the Y value. All right? So coordinates for point A, it's going to be the same all the way down. It's going to be -3, 9. For B, it's going to change depending on where your B ended up. All right? But you can see, hopefully, that the 2 points are getting closer and closer to one another. All right? And so at some point, what you're going to do is follow the trend. If you complete the table correctly, you're going to follow the trend and come up with the would-be secant 6. You're not actually going to draw it, but you'll be able to determine what that slope is, or that slope would become, and that chart is going to help you kind of discover some rules related to what we call differential calculus. All right, so you're going to work on that. Try to make some progress on this, the top half of the second page. If you get stuck there, I kind of, at least for today, I kind of sort of want you to get a little stuck there and see if you can make your way through it. Tomorrow in the beginning, I'm not going to leave you hanging. Tomorrow in the beginning of the class, we'll debrief on this page, and I'll get you oriented on the top of the second page, and then you'll carry out from there. All right? But the idea is for you to try to discover as much of this on your own without me handing it to you, because that's going to help the learning. I promise you. The people who take this activity seriously, at the end of the year, they look back. This has happened over the years. They've looked back and said, this is the activity that helped them understand calculus all the way through. All right? That's how important it is. For you also. So these are all -3.
Mr. Can, how do you do distance?
y2 minus x2 minus x1 squared.
Correct, but that's if it's like a diagonal distance. This distance is just a horizontal distance. So you're just looking for the difference between the b value and the a value. Because in the first case, it's 2, 4, right?
Yeah. Well, I really like how this works out. It's very
So for the
nice.
first one, it's 5.
So it's just 5 plus 16.
I'll take a picture of the coordinates
Say it again? Yeah, I'm gonna kind of get you try it on your own first, but if you get stuck, I'll help you tomorrow.
We honest, I'm not a.
So in terms of the completion of the table, the b value should have been easy because those are just the x values of all the coordinates as you get closer and closer to the a value. So the next one would be 1, then 0, and so on, right? But you notice a trend, right? So 1, 0, if you follow that trend, it seems to be decreasing by 1 every step of the way. So -1, -2, -3. The b value was at 4, then it became a 1, then a 0, then a 1, a 4, and a 9. So eventually in the last row, you had the a f of a, the b f of b being exactly the same coordinates. All right? So if there are two coordinates that are exactly the same location, but you still want a line to go through that location, that line would have to be a tangent line. All right? All right? So then, as far as the h values are concerned, h is just the horizontal distance separating your x values, which we're calling a and b. So 1 minus -3 is 4. 0 minus -3 is 3. Follow the trend, we're decreasing by 1 every step of the way. Until eventually, very important observation here, there's 0 distance between the two x values. All right, so then the slope is change in y over change in x. Whether you use the table or not, I mean, I guess that's entirely up to you, but if you really think about it, we got the change in x already, that's the h. The change in y is just the difference between f of b and f of a. All right? So if I just subtract my f of b, f of a, I'm going to get my change in y values. All right? 4 minus 9 is -5, divided by h would be -1. All right? 1 minus 9 is -8, divided by 4 is -2. Follow the trend. Once you get a few values in there, you get -3, -4, -5. Now, if you do the calculation tells you indeterminate. But if you follow the trend straight on down the line, what should the next number be based off of that trend? -6. So what we just got is the slope of the line tangent to the curve. At the coordinate -3, 9. So the top of the next page just deals with coming up with a general structure for this, because what we don't want to do is have to create a table every single time we want to find the slope of a tangent line. There's got to be an easier way. So that's a teaser for tomorrow.
So for 14, it says